Hey, the fun never stops. So, these are, this is the projectile motion question. Yeah. Okay, launched horizontally. Questions 13 through 16. The introduction to this says that I place a mass M on that. No, it isn't. I'm looking at the wrong one. Oh my gosh. Some people, oh, that's it. Okay, 13 through 16. A boulder of mass M rolls horizontally off a cliff, height H. Exhibit A, with a horizontal speed of v naught. And the boulder lands a horizontal distance r from the base of the cliff. Ignore air resistance, at least for the first part of it, right? So it says in question 13, for the following two questions, whoops, that's a typo. For the following questions, for the following two questions, describe how the time in the air and the range of the projectile would be affected. Be sure you can support your answer. It's not a typo. If the mass of the boulder were doubled, remember that ignoring air resistance, the mass and thereby the weight have nothing to do with this. So this thing has mass m, and if it were mass 2m, it would still land in the same place. The way that you will see that on a test likely is you have one boulder of mass m, and then you might have a second boulder of mass, going side by side of mass 2m, and then they might have you rank where they would land. And if they're both moving with the same velocity, and you'll rank, whether or not the range for 2m would be shorter, equal to, or greater than that of m. And of course, they land in the same spot, ignoring air resistance, because acceleration due to gravity, what we were just talking about in the previous video, acceleration due to gravity, good old Galileo, is independent of that mass and its weight. Okay. So they land in the same spot, same time in the air, because the time is going to be based on how high it is and an acceleration of a negative 9.8, and the fact that the initial velocity in the air is v sub 0 y of 0. V sub 0 y of 0, it's going to fall that negative vertical displacement, and acceleration is negative 9.8. So that's the time. Be the same no matter what the mass is. Mass isn't in the equation at all. And then the range would be the same, because the range will be v sub 0x times t, and t is not changed, and the v sub 0x is not changed. Ta-da! They'd be the same. If the initial horizontal velocity in the air were doubled, if you double that, keep in mind that the only equation in the x-axis that we are responsible for is v sub 0x times t, and that is horizontal, so that is v sub 0x. Okay, so that is v sub 0x, because the initial velocity is horizontal, and you double that, you double that. They're directly proportional to each other. Okay, so if you doubled the velocity, the range would double. What about the time? You didn't change the height. The time's based on the height. And you didn't change the downward or upward velocity. The initial velocity in the air in the y-axis is still 0. So you haven't changed that just because you doubled the launch velocity horizontally. You haven't doubled that because it's still horizontal. So that's still 0. Acceleration is still negative 9.8. The height's the same, so the time would be the same. Time doesn't change, but that does double, so the range would double. Yeah, we're having fun now. Oh, yeah. Question 15, the boulder is now launched with the same initial speed from the same good old cliff, high cliff, but with an initial upward angle of 50 degrees above horizontal. How would this affect the following? So, I will follow you, the following. So it's going to go, whoa, it's going to go up at an angle like that. Okay, so there's the initial velocity going that away. And, okay. Here we go. How would it affect the time in the air? Well, gosh, it's going to take longer, right? Because it's got to go up and then go down. So in the previous one, it just went down through a vertical displacement of like negative h, right? But now it's going to go up a little bit further and go down. Remember, time's going to be solved in the y-axis, and it goes up first and then comes down. So it's going to take longer, right? Most definitely. How does that affect the acceleration in the air after it's launched in the air, after it's launched before it hits the ground? It doesn't, right? It doesn't affect the time, the acceleration. The acceleration in the air is always negative g. How about the speed with which it strikes the ground? This is actually an energy question, really. Remember that we did this in class. If I launch this thing with some speed horizontally, if I launch it with some speed upwards, if I launch it with the same speed downwards, if launch with the same speed from the same height, it's going to hit the ground with the exact same speed in all those situations. I mean, greater than your launch speed. It's going to pick up speed, but it can hit the ground with the same speed, whether I throw it downward, sideways, or up at an angle. All right. And that's an energy thing. Remember, we did this with, again, I said we did this in energy, kinetic energy, because it doesn't, I'm getting tongue-tied. The time in the air would be different. Where it lands would be different. The angle with which it strikes the ground would be different, but the speed would be the same. Okay? The kinetic energy is based on its speed, not its direction. Kinetic energy has no direction built into it. So it has the same kinetic energy up here, no matter which way you throw it. It has the same potential energy because you launched it from the same height. And those are the only two variables that matter in the initial condition. And in the final condition, its potential energy is 0, and it's going to have a final kinetic energy. And that's where that final speed comes from. You haven't changed anything in terms of energy, just because you changed the angle. All right. Now, so the speed strikes the ground, be the exact same value. If air resistance were not negligible, then how would that affect the horizontal component of the velocity? Well, we have assumed in all of our calculations that this is true because there's no acceleration in the horizontal, and that this stays constant. So you're able to say, as this thing travels through the air, that Vx is just equal to V sub 0 x, because there's been no horizontal acceleration. But what if you had like a resistive force? So I'll put a negative there because it's going to slow the thing down as time goes on. The horizontal velocity would decrease because air resistance is causing a negative acceleration as it moves over. So it gets slower and slower and slower. Okay, hopefully that makes sense. So how would it affect the horizontal component of velocity? It would slow it down. It would decrease it. How about the time in the air? It would increase the time in the air as it's falling because its acceleration, the rate at which it's getting faster on the way down, that would be decreasing. Okay, all right. It's still falling and it's still speeding up, but the rate at which it's speeding up is decreasing. So so your acceleration is decreasing, and eventually it might hit terminal velocity, which means it stops speeding up. It just keeps falling with the same speed. It's going to take longer to fall. How about the net force in the vertical axis as the projectile falls? Well, in the vertical axis, you've got, let's use a different color here. In the y-axis, as this thing falls, of course, you have gravity the entire time. But as it gets faster, you have some sort of resistive force that's increasing. So net force in the y-axis is going to be, I'm just going to do weight minus r. At first, if there's no air resistance, then that's the force that causes the acceleration. That is the net force. But then it starts to speed up, and the faster it goes, the greater the resistive force. That gets bigger and bigger and bigger the faster it goes. That still equals m times a. But the bigger that is, the smaller this interval gets, the less that is. And so the further it falls, the faster it goes, the greater the resistive force, the less the acceleration, all right? Therefore, the less the net force. Again, though it still weighs the same, but this is proportional to how fast it's going. So the faster it goes, this these two get closer and closer to each other. Eventually, if it has the opportunity, if it travels far enough, they become equal to each other, and therefore the net force is 0. It's still falling, but that's when it's falling with constant terminal, what we call terminal velocity. It's falling with constant velocity at that point. Okay, so to answer that last question in a nutshell, the net force in the vertical axis as the projectile falls decreases. It gets less and less and less as it falls. Okay, the net force does. Difference between those two.